I'd like to invite Jim Heppelmann to the stage, talk a little bit about the partnership and about the exciting things that PTC offers as part of the ecosystem.
Great. Thank you, Blake.
Jim?
How you doing?
So it's been quite a ride this year.
It has been a very big year, I think, for both companies. A lot of excitement and a lot of excitement ahead of us still.
That's right. You know, as we start to engage, and of course we've got big parts of our organization, you know, fully involved from the sales side to the back office, the development teams working together. I think the thing that gives me the greatest satisfaction is the early response from customers across a wide variety of industries.
Yeah, I mean, I think, you know, Rockwell represents like 35,000 companies and PTC about 30,000. And I've not gone anywhere where this story hasn't been, you know, well received and a lot of excitement. So I think it's the customers are excited because we can unlock so much value. I think the employees on both sides are very excited because they see really an interesting, probably winning strategy, you know, in the industry developing here. So certainly a moment of a lot of energy and excitement.
Yeah, and we got there in a hurry, and we're open for business today. So
yeah, let me just say, Blake, you know, in an industry full of meaningless partnerships, this one means a lot. So
absolutely.
we really appreciate that.
That's right.
Thank you. So I'm very excited to have this opportunity today to talk about my favorite topic, which is digital transformation in the manufacturing or industrial world. And I want to introduce you to PTC. And I think as you see PTC's aspirations, you're going to understand why we're partnered with Rockwell, because it really is a marriage made in heaven. So let me start by turning the clock back 1 year. So 1 year ago today, I was at this forum. I was introduced briefly, but I was mostly incognito because we signed the partnership of the June version. But I was at the forum incognito because we were talking to each other already. And 1 year ago, PTC and Rockwell were completely independent and completely unaligned companies. So PTC is a large industrial software company. 30 years ago, for example, we pioneered the concept of 3D computer-aided design with a very famous product called Pro Engineer at the time. Now it's called Creo. 20 years ago, we pioneered the concept of web-based product lifecycle management. And then starting about 5 years ago, we made some big investments in IoT and industrial connectivity and augmented and virtual reality headed toward IT, and an IT company headed toward OT. Both of us probably have visions that are bigger than our ability to execute, but if you align us together, and amazing things happen. And that is, we can produce now a suite called Factory Talk Innovation Suite that truly lives where IT meets OT. This is like, in a way, like the Microsoft Office suite for IT-OT convergence. It's not Word and Excel and PowerPoint. It's IoT and AR and connectivity and analytics and MES, all working together in one beautiful, well-integrated suite. And there's nothing like it in the industry. So this is a special moment for both of us. Now I want to back up a level and talk again about digital transformation. I didn't really come here to talk about products. More like, what are we trying to do and why? And if you think about digital transformation, I think one of the places GE didn't get it quite right is it doesn't mean you go to bed as an industrial company and you wake up as a software company. That's actually not the point. The point is using digital technologies, cloud, analytics, artificial intelligence, IoT, augmented reality, virtual reality, automation, you know, a long list of digital technologies to transform an industrial company into a better industrial company. So to me, digital transformation is the process by which an industrial enterprise becomes a connected enterprise. So let me tell you about how PTC has thought about this, and again, hopefully you'll see crystal clear why we've aligned with Rockwell. Let's start with how much money is being spent in the quest for digital transformation. So the industry analyst firm IDC published a report recently that said in 2018, enterprises around the world will spend $1 trillion under the heading or under the pursuit of digital transformation. And about 30% of that, so $300 billion, will be spent in the industrial world of discrete and process manufacturing. That's where Rockwell lives, that's where PTC lives, that's where many of our customers, and most of you in the room, frankly, live. So if you're going to spend $300 billion, you must be aiming for something big. And I think, again, what it is, it's differentiated products and brand promises. It is, productivity and efficiency that's at a high level and increasing constantly. And it's flexibility and agility, because the world's moving fast, the clock speed's so fast, and companies that can shift with it really get an advantage. So that's what people are spending money on. The question is, what do they do? And so if you think about an industrial or manufacturing enterprise, separate and distinct from a bank or a hospital or a school, there are certain things that industrial enterprises can pursue that are unique to this discussion. I think there are three main vectors by which industrial enterprises can transform themselves. First, they can think about their products. You can produce very different products because of digital transformation. The second thing is, look at your processes and business processes. And of course, production and supply chain, but also customer support and service. These are very important processes in the industrial world, and you can use digital technologies to change them radically. And then the third thing is you can transform people. Now, I'm really talking about transforming the capabilities of people, but really turning people at some level into cyborgs. And I'm going to talk about this as I get into the meat of my presentation. I want to start with products, which of course is a place that I've spent much of my career, is helping people design products. And I want to talk about what could you do with products using technologies like high-performance computing, artificial intelligence, additive manufacturing, and so forth. So here's a typical engineering design, a little bracket that holds a shaft. And we can simulate it and make sure it's good and strong. Blue means low stress, green means a little bit of stress. But overall, we're pretty good with this design. And this is the way a human would have made this design for decades, frankly. Now, what if we said, now we have computers that have so much power, GPUs that run analytics or artificial intelligence code 400 times faster than CPUs. And what about farms of GPUs up in the cloud? We could do some amazing things, for example, by letting artificial intelligence try to solve this design problem. So a human sets it up and says, I want to anchor this part where those 4 smaller blue circles are. Think of those as bolt holes. And then I want to put this shaft through where the 2 blue, let's call them bearings are, and there's going to be a load on this shaft. Shaft's going to be turning, and it's going to carry a load. Okay, I want to build it in a casting process. So knock yourself out and see what you can come up with. And very quickly, the algorithms say, this is the best design. By the way, I gave it the envelope of the old part to work within, and see how little of the material is actually necessary for an optimized casted part. So really, the human design was pretty inefficient. Too much material consumed, weighed too much, etc. We could have made it like this. Or I might say, actually, I changed my mind. I want to forge the part. Give me a part that I could make in a forging process. And again, the artificial intelligence takes over and says, okay, then I'd use this geometry. And of course, I need these separation lines. So after the part is punched in a press, I can separate it and pull it out of the dies. It doesn't stick into them or anything like that. So that's an example of a forging process. What if I said, hey, knock yourself out loose, or knock yourself out with a additive design process? What would I get? This is really interesting, because now I get a geometry that a human couldn't model in months because it's so intricate and complicated. So here you see there's a tremendous amount of air in this part. It's a very, very strong, efficient design that could only be produced with additive manufacturing. Now, I could imagine that part would get all gummed up with, grease and dirt and so forth. So I might say, do the same thing, but please wrap a shell around it just to keep it, a little bit cleaner and prettier looking and so forth. So here's now the same part, again, created by artificial intelligence. If we cross-section this here in a second, you'll see, again, the detail inside is unbelievable. You could only print this part. But if you did print it, it would be a very lightweight, very strong part, And of course, that's a radically different manufacturing process when we get downstream. So those are some examples of artificial intelligence leading the way. Let me show you a different example of artificial intelligence, or really real-time simulation, helping me design. So this is a Polaris snowmobile, and we're going to zoom in on a part, which happens to be this extruded part that connects the ski to the frame. And if you look, if we turn simulation on, the red here is bad, and we're looking at deformation. That part's moving around a lot. And if we flip to a stress plot view, up in that upper left part of the part, there's a big stress concentration. This part's probably going to break, so we have to make a lot of spares, unless I could modify the design. So now, as a human modification, I'm adding this sort of X-shaped brace into the extrusion. And I'm aligning the front and the back. That takes a second. And as soon as I commit those changes, it's automatically reanalyzed. Now, and by the way, we solved the problem. Now, hopefully you see that this is a bit like the way spell checkers work these days in Microsoft Word. You know, the way it used to work is you'd type 20 pages of content, then you'd stop and run the spell checker, and it would give you 10 pages of errors that you'd have to go fix. Now the way it works is it checks as you type. You can be halfway through a misspelling, and it's already complaining. So now, using high-performance computing and real-time simulation, because we had to mesh that part automatically, simulate it using a finite element analysis, and bring the results back and color code the part again, all within a second or two when you committed the change. So a huge amount of high-performance computing. This is actually using ANSYS real-time simulation technology called Discovery Live that's built into PTC's CAD system now, and so forth. So very, very exciting. Now, I want to take it to the next level and show you how you could combine human and artificial intelligence. But first, I have to take a detour through a concept that I think is really important, and that is the ability to create parts that look like Mother Nature created them. So let me talk about that for a second, because I want to compare what Mother Nature does versus what people do. And so here, for example, are two flying machines. Mother Nature's flying machine, man's flying machine. If you look at the wing, look at the detail and the intricate design of Mother Nature. Look at the ribs and spars and so forth, how much more complicated they are. The strategies for lightening the part and making it very strong but lightweight. So Mother Nature on the left uses an additive process. And she can create unbelievable solutions, for example, for capturing energy, capturing and storing energy, or for moving fluids and gases around. So if you look, in almost every case, the design from humans is a crude approximation of something they saw from Mother Nature. The problem is humans have been using a subtractive process versus an additive process. And Mother Nature builds from the inside out, and of course humans build by subtracting from a sheet of steel or a block of metal or what have you. So the human design ends up being, again, crude approximation, constant diameter, whereas there's a tremendous amount of variable diameters, rigid materials instead of flexible, cellular things and so forth. So what if we could combine the best of human intelligence, the best of artificial intelligence, with an additive process that would produce some very, very interesting parts? So I'm going to use this next example as a Triumph motorcycle. And the important thing to realize about this Triumph motorcycle is that it's beautiful. And anything you do that makes it better but less beautiful would be bad, okay? So in this particular case, I'm going to focus on this swing arm that connects the rear wheel back to the chassis. It's a 5-part assembly, 6 if you include that little bracket. In a CAD system, looks like this, 2 bent steel parts, 3 castings. What if I wanted to make it into one single part to eliminate the supply chain and so forth? I would say I want it to look pretty. So I'm going to specify the outside cosmetic look and then turn the algorithms loose, given the loads and so forth, to calculate what should the internal structure be, back to the lightning holes and all that kind of stuff. And so the algorithms run, and they say, well, where would load be carried in that volume? And really only where this blue material is. So you can see most of the volume actually has no load in it. To put material there is just a waste time printing it. This is the actual useful load, or useful material. So now we convert this back to a full CAD model, and we end up with a part that's beautiful on the outside, and frankly looks a bit like that bird on the inside. If you look, it'll end here in a second, and we'll look at it. The outside structure, beautiful. That's the human's contribution. The inside structure, efficient and powerful. That's the algorithmic contribution of, let's say, artificial intelligence. And if you look at this inside, it's very intricate, very interesting. Frankly, it's not symmetric because there's a drive chain on one side and not the other, so it's asymmetric loading. So a fully optimized part that we can print quickly, efficiently. It'll be lightweight and very, very strong. So I think that's an interesting example of human, artificial, additive all coming together, in a single new part that we want to use. So far I've been talking about products from the physical perspective, physical parts. But probably an even bigger trend is what's happening to the digital parts of products. And this chart comes from some papers that I published with Professor Porter years ago, actually. But we said if you just think of the evolution of a product over a period of decades, something really interesting has happened. And it was modeled after a John Deere tractor because John Deere was PTC's first ever customer 30 years ago. And maybe you think tractors are simple. Well, wait a minute. They used to be kind of simple. So 30 years ago, a tractor was a mechanical-only beast. You could model every single part in a computer-aided design system. You got the full bill of material, everything, simple. But what happened is software started to creep into this tractor when it became a smart tractor. So software came into the engine for an engine control unit. Software came into the cockpit for digital gauges and displays. And suddenly we had a smart tractor. Then John Deere literally said, why not, if this tractor has CPUs running software, why not give it an IP address in some form of connectivity and let it connect back to us? Because then we could monitor it, we'd know what it was doing, we'd know how often it was used, we'd know if it needs service or oil change or more fuel or what have you. Be very interesting. So that's the smart connected product. Lots of digital stuff at this point now because the tractor has a presence in the field, but also now a presence up in the cloud, and these two identities are talking to each other and so forth. You take it to the next level. Wouldn't it be great if all the different products used on a farm shared data with each other? So for example, the harvesting equipment could keep track of how productivity varied over the acreage, and that information could inform fertilizing equipment next spring, put a little bit more fertilizer where yield was low and maybe a little less where it was high. And then if we had GPS-based precision tracking, we could also put the, let's say we're planting corn, we could put the fertilizer in a narrow strip knowing that in the next pass, the planter will land the seeds in that exact same strip. Because we wouldn't want to accidentally fertilize the weeds between the rows. We want to fertilize just the rows. So if you take this idea, you start to get some real efficiency. Much less input, much more output. Very, very good for everybody. But then you take it to the next level. And you say, well, what farm has only farm equipment? You might have irrigation equipment that could be informed by weather systems. You could have seed strategies for different hybrids and so forth for different areas depending on the soil. Of course, you might have animals. Who knows? Just a tremendous amount of stuff. And how could we implement a system of systems that would make all this stuff work together? So this takes you to smart farms, it takes you to smart cities, and frankly, it takes you to smart factories and smart plants. Because every factory or plant really is a system of systems where we want to gather data from many subsystems, integrate it all together, and make it all work better, more effectively, more efficiently. So that's a pretty interesting strategy. Let me show you the benefits of doing that. So really, this tries to say, what do you get when you make a product smart and connected that you didn't otherwise get? Well, first you get monitoring. Basically, you get a feedback loop. So you can monitor what's going on. You can control what's going on, possibly steer it, control the application of fertilizer in different areas of the field, control lots of different things by having a bidirectional conversation. You could add algorithms that optimize. In a lot of buildings right now, you don't just push up or down on the elevator anymore. You say which floor you want to go to. And then it says, well, then the optimum elevator, all things considered, to get you to the 13th floor would be this one, elevator B. So go to elevator B, and trust me, it'll stop at the 13th floor. So that's an example of optimization. And then the ultimate goal is autonomy. And of course, we are seeing autonomous tractors, but autonomous robots, autonomous automobiles, lots of stuff. That's like the holy grail of total use of IoT type of technology. So let me talk about a couple of customer examples here. So Colfax is a customer of PTC's using our ThingWorx technology, by the way, running on Microsoft's Azure cloud. So Colfax makes, amongst other things, welders, ESAB welders. So they might be used in a production plant. They might be used out in the field in a repair situation. They could be used in some kind of a fabrication process. They might be used in a custom shop for customizing automobiles. But in each case, they might be used in construction. In each case, I'd like to gather data, volts, amps, but how are they used? When are they used? How well do they work? What problems develop? Where are opportunities with consumables? And I'd like to take that feedback loop to the connected enterprise and say, this data surely is useful to the engineering department, could be useful to the manufacturing department, certainly is useful to sales and marketing to know how your products are used, and frankly, if they're highly utilized, it's probably time to sell some more. And then the customer operations, or customer success, if you want, or service departments could get a huge amount of use. So now we're talking about products with built-in feedback loops, really transforming the way a connected enterprise thinks. I mean, taken to the nth degree, you might start selling welders as a service, product as a service. I'll pay you for the time I spend using, or I'll charge you, flip it around, I'll charge you for the use of the welder. You don't have to buy it anymore. So that's a strategy that's happening as well, at the business level of connected enterprises. Okay, so that closes out my first part of the talk on products. And I showed you a lot of stuff, high-performance computing, driving real-time simulation and artificial intelligence, driving generative design strategies, the role of additive manufacturing, and of course, the huge role of connectivity, smart connected products, smart connected systems, and systems of systems using industrial IoT technology. So all of this stuff I've talked about comes into the partnership. Now, Rockwell will sell much of this through the innovation suite, and PTC can sell the rest, but as a Rockwell customer, everything I'm talking about now, either directly or through the Rockwell into PTC relationship, is available to you. Let me move on to where Rockwell really has depth, which is in processes, in particular, again, in production, supply chain, processes like that. So if you look at the way these processes work today, there's no shortage of digital technology already. In fact, Rockwell supplies much of it. Of course, there are competitors to Rockwell that might supply it as well. So there's level 1 PLCs, there's level 2 HMI SCADA systems, level 3 MES and MOM systems, and then of course level 4 enterprise systems, including PLM systems like what PTC makes, but also ERP, supply chain, what have you. And they all have information. There's a couple problems though, and that is there's a lot of information that's in none of these systems, and the systems here aren't that well integrated together. They're a little bit too much silo-based. So you have to hunt and peck around trying to piece together what's actually happening if you want to get the problem solved. So we end up with some challenges. Now, where industrial IoT technologies come in is sort of a wrap and extend model. So ThingWorx, for example, comes in and connects to everything. It connects to PLCs, into HMI SCADA, into MES systems. It connects to enterprise systems, supply chain, ERP, PLM if you want. And it also, by the way, connects to sensors that maybe are added just for purposes of smart factories, not connected into any of those other systems. It connects to environmental sensing systems, humidity, temperature, what have you, that might be important to know. It connects to logistics and barcode and RFID systems. It connects to supply chain capabilities. And it pieces together all of this data into a picture that's never been seen before. So we call that source and then contextualize. So contextualize means create a model that helps me understand a unified perspective across this environment. Now let me develop applications and use analytics against the data in those applications so that I can make both assets more productive and unlikely to go down unexpectedly, and make processes more efficient. And I can do this on the edge or the cloud or some combination of the two. So again, the ability to produce role-based experiences that give you real-time visibility, predictive maintenance capabilities, and just generally speaking, a very flexible environment. One of the reasons it's flexible is that you can produce the same applications that work in different factories whose technology stack's very different. So maybe one factory has Rockwell technology, another factory has Siemens, but you as a plant manager would see a unified view across them. So it's really a platform that embraces the heterogeneity and messiness that's in this world and tries to bring it all together and produce a more efficient, effective capability. So let's take a look at some examples of what we're doing together with Rockwell. And this is an example you might have seen. It's a Rockwell system, sort of a filling system, filtering, filling type of system. Lots of OT technology moving around here, different robotic systems and so forth. But using ThingWorx, we're drawing data from everything into the IT side of the world, bringing it together on an edge server or what have you, and giving the plant manager and other roles within the plant a picture of what's going on. So for example, here's line 1 and line 2. I can quickly see there was a problem on line 2 because the icon's red. What do I do about it? Let me drill in and understand and get to the point where I'm using analytics, for example, to explore the problem, try to get to the root of what it is. So you'll see inside this ThingWorx software is FactoryTalk Analytics. So these bar charts and so forth are Rockwell software running inside PTC software to help you dig in and analyze. And you can see there was a step up in bad parts produced at a certain timestamp and beyond. So something went wrong. We can drill down, go explore what it is. We can see a couple of strange looking bars in the bar charts that we probably ought to drill deeper into. That might lead us to a conclusion that we need to do some maintenance activity. So we should go fix these machines before they really go down and take the whole line down with them. We can launch work activities in a maintenance management system or a work task scheduling system and so forth, and produce the data that you'd need to use to go fix that particular problem. So that's an example. A couple other quick stories. Rockline is a Rockwell customer who, using technology like this, has applied it to their manufacturing cells. And instead of doing manual data collection and trying to bring it all together, they now do it automatically real time, and they've been able to increase OEE by more than 20%. Another Rockwell customer is ASA, Arkansas Steel, who's producing specially formulated steel parts for railway use, and again, replacing a slow, expensive manual data collection process with a real-time automated one that has very quickly increased their yield by 3 percentage points. So on the process side, I hope I've convinced you that with industrial IoT technology, with artificial intelligence and analytics, and with hybrid cloud edge architectures, we can do amazing things to make plants and factories and things like plants and factories run much more efficiently. So now let me move on to the last piece, which is people. And this is probably my favorite piece because I think people are heavily underserved to this point by digital technology. Let me start with the problem. The problem is largely this retiring workforce problem because we're losing workers at a faster rate, thanks to baby boom retirement, than we can recruit back. Blake mentioned it's hard to get people into these jobs. They're not cool enough in terms of tech. And the second thing is it's very hard to train them. So for example, the Manufacturing Institute, which is an arm of the NAM, the National Association of Manufacturers, did a study with Deloitte that said by 2025, 3.5 million workers will retire, but we'll only succeed in replacing 1.5 million of them. What will we do for the other 2 million? We need to lure more people in. We need to increase productivity. By the way, their study says it takes 70 days on average to train an industrial worker. So how can we fix that? One way to fix it is to throw money at it. So Boeing has a strategy where they're spending $100 million on worker training. And I included this anecdote just to show you it's big money. But the reason Boeing's doing this, there was a story you probably heard maybe a month or 2 months ago about Boeing trying to lure back retired production workers to the 737 production line because the order book is huge, but the lines are slowing down because they're losing workers and struggling to backfill. So they're begging the retired workers, please come back. We'll pay you more, whatever it takes to get you back in the game. So it's an expensive, difficult problem. And I mentioned that information technology has not served humans well thus far. I mean, we've not done a good job of helping humans participate in it. And so let me say, if you think about all of the employees in an industrial company, the workers, they either on the y-axis, they work in an office behind a desk with a big computer or a little computer, or they work out in the field, in a factory, in a plant, on a service call, at the customer, installation site, what have you. And if you think about the type of work they're doing, it's either simple and routine, like let's say accounting is, I mean, like in accounting, it's not maybe simple, but you don't get rewarded for creativity really either. I mean, you're supposed to just follow the rules accurately, and the auditors are going to audit whether or not you did, so, you know. Or maybe it's complex and variable. So, for example, engineering might be in that lower right box, where the work is very complex, but it mostly happens in an office behind a big, strong computer. So if you think about this, I would argue the left column is well served by laptops and then mobile, even paper. The bottom row is well served by computers. It's that upper right box that's a big problem. Here I'm talking about 737 production workers who are building 737s, and each one can have a different configuration than the previous one, and they're building them in a factory. And the answer isn't to give them a big computer. They need a different way because they're working actually on an airframe. And so what do? They don't want paper, they don't want a mobile device, they don't want a computer. What do? And before I tell you what I think we should do, let me just remind you that probably at Boeing, the majority of the employees of the Boeing company work in that upper right box. So we're talking lots of people. I think the answer is augmented and to a lesser degree virtual reality. Now let me try to introduce the concept of AR and then talk about why I think it's the answer. So AR means bringing digital technology into the field of view, particularly for an industrial worker, and making it part of the scenery. So I have a couple of examples I sort of want to talk through here. Let's imagine there's some big, powerful digital cloud out there, and there is, several of them, many of them. I remember paper punch tapes as the way you brought, for example, a toolpath to a machine. You punched it out a byte at a time on a 1-inch wide paper tape, carried that to the machine, and read it in through a tape reader. Think of how much that's changed to the type of real-time control Rockwell provides today, for example. It's amazing. Analytics, real-time control, you know, very, very sophisticated connectivity. Now let's look at people for a minute. And just to pull out my iPhone here. When I run an app on my iPhone, it isn't, frankly, much different from the first app I ever ran on a Macintosh 30 years ago. It's changed a little bit. The form factor of the phone's different. The graphics are a little bit slicker. But the whole idea of a flat graphical user interface that uses text and icons to communicate to me is pretty much unchanged. So I'd argue humans are kind of back at the paper tape level, having only progressed a little bit. Well, why is that? Well, the problem is humans don't have an Ethernet port like robots do. Humans have 5 ports in their analog. So the first port is taste. Pretty hard to give you digital information through taste. The second port is smell. Only one example I can think of is the smell that's artificially put in natural gas or propane so that if it leaks, you smell it. Actually, natural gas and propane don't have a smell, but we put a chemical in there to communicate to you, if you smell this smell, then you know gas is leaking, please be careful. But I can only think of one example. Touch is the third sense, and of course, Braille would be a classic example of encoding digital data into a medium that you can interpret through touch. Not very effective, though, as a way to communicate digital cloud to people. How about hearing? Well, hearing's much better, much better, but I'd argue very slow. So hearing would include Alexa and Siri and any kind of voicemail system you talk to and so forth. But it's very slow, on the order of 3 words per second, which I defend by saying 1001 as a way to count off a second. That's 3 words, 1 second. I maybe could say 1001, you know, really, really fast and squeeze in 4 or 5 words. But basically, it's a very slow medium to encode and decode data. In computer parlance, it's not much better than paper tape, okay? And that brings us then to the 5th sense, which is sight. And sight is lightning fast if you use it right. So I often say, do this little thought exercise. Close your eyes, open them for 1 second, look around, and close them again. And think of how much information you ingested. You realize you're in a room. It's a large room with many people, lots of interesting lights. There's a speaker in front of on a stage, in front of big presentation slides and so forth. That's a tremendous amount of information in 1 second. So much so that the problem isn't ingesting it, it's remembering it, because your ingestion speed is much faster than your data storage here. So what if we could take digital information? Well, before I do that, let me say, the problem is if you look at this flat screen for 1 second, you get about 3 words, because very few people can read off a flat screen any faster than they can speak. I mean, again, maybe slightly faster, but not orders of magnitude faster. And we need many orders of magnitude improvement here. So really, augmented reality is about taking digital data and using, in particular, your sight and hearing, and to make that data part of the scenery. Now, before I go any further, let me just say, traffic signs are augmented reality. Putting a stoplight in an intersection is putting in that intersection, in the context of that intersection, a mechanism to pass information on to you. Please do not drive through this intersection right now because the light's red. Now, because it's in context, you don't have to think about it. Like if you got a text every time you're supposed to stop, it'd be a bad situation, right? So the thing about the stoplight is it's so familiar, you process it without thinking about it. And that's the key thing, is process without really thinking about it, studying it, concentrating on it. Stop signs are the same example. A sign that says there's a sharp curve coming up. Well, if we gave you that sign 5 miles ahead of time, it would be useless. We need to put it in context just before the sharp curve comes up to make sure that you're aware instinctively that there's a sharp sign coming up, or sharp turn coming up. So augmented, or let me say traffic signs, stoplights, whatever, are augmented reality. It's just they're done with physical medium, which is not very scalable, very expensive. So what if we could do the same concept with digital technology? The problem is, again, these analog ports. So what do we need? We need a modem. And I think that a HoloLens, for example, is a modem. Now, this doesn't work, by the way, when I'm talking to younger people, but I think here in the room, most of you remember what a modem is. It stands for modulate, demodulate, and it converts analog signals to digital and digital signals to analog. Originally, so that digital mainframes could send information over analog telephone lines, and it'd get converted to digital at the other end, so it could be displayed on a terminal or what have you. And then somebody could type in on the terminal, we'd convert that back to analog, ship it across the country, convert it back to digital, and say give it to the server or mainframe, whatever. So what a HoloLens does is it converts digital data to sight and sound that's part of the scenery. And then it converts voice commands, or hand motions back to digital data that goes back to the other end again. So it's a very interesting concept. And just to show you a quick example, I made this video myself, so it's not very good, but I didn't really have the means to show you a live demo, but you'll see me here in a second. This is what you would see looking at a motorcycle. So I happen to be using my iPhone here, simply because that does the same processing that a HoloLens would do. But for example, you saw how much fuel's in the tank and so forth. Here on the right side, you see 1, 2, 3, 4, and I can step through and get some instructions as an operator. Here's the clutch lever. Number 2, there's a tool set under the seat right about here. Number 3, there's a handbrake on the right side that operates the front wheel. Number 4, there's an ignition and steering lock that you're going to need to deal with, and so forth. So that's the concept of augmented reality. Let me introduce the sibling concept of virtual or mixed reality. So now, rather than focusing on that physical motorcycle, I'm going to introduce its digital twin into the scene. So now I have a hypothetical digital motorcycle. In fact, I can take away the plastic one, and I can interact with the motorcycle that maybe I'm supposed to service tomorrow 1,000 miles away. I can understand it, practice it, know what I'll experience when I get there. Okay, there's a problem with this swing arm. Show me what the analytics say. There's a swing arm deviation that's unexpected. Okay, show me how I would go about repairing it. And it says, please take off this rear brake caliper first, and it goes on, but the recording stops here, just for brevity's sake. So AR allows humans to see digital data that would otherwise be invisible. For example, how's air flowing in this room? Oh, I could use air lines, computational fluid dynamics, and visualize air. I can visualize how much fuel's in the tank, how much pressure's in the tires. I can visualize all kinds of things. We can provide instruction. Show me what to do, and I can instead of giving you a PDF paper on the side, no, I'll put that information right on the motorcycle. I could give you a way to interact with the product. I didn't do that with that motorcycle demo, but I could have said, start, and the motorcycle would have started. Stop, and the motorcycle would stop. Or how much fuel do you have? And it would answer me, again, using voice commands and so forth. And then with VR, we could add this capability to simulate an environment. Simulate a factory, simulate a product, simulate a situation, so I can go there virtually and see what it's all about, either because I want to go to some distant place, or maybe I want to go back in time. Take me to this robot last week just before it failed and help me understand what was going on and why it failed. Okay, that's interesting. And I could use it also for scale. Let me become an air particle and fly through an engine to understand how it works. That's something else I could do with virtual reality. So anyway, I think the concept here is very powerful. I want to show you a couple of more practical examples. This is BAE Systems using CAD data as a way to provide work instructions to a assembly worker. So this worker's put on their HoloLens, and they're assembling, by the way, batteries that go in hybrid buses. So you'll see the digital information floating in space ahead of this woman. And so she's just replicating what she sees while keeping her hands free and keeping focused on the work in front of her. And she goes through a process step by step of assembling this machine. So click on the right one for the next step. Here are all the remaining components. And then when we're done, assembly complete, and we actually have a record that you did it all. Frankly, we watched you do it all using the cameras on the HoloLens. So that's one example of work instructions. Let me give you an example, kind of a demo here designed to communicate how do we solve the retiring worker problem. So there's 3 phases. First, the retiring worker is asked to put on the HoloLens and do their job. And so they run a piece of software called Waypoint, that's PTC software, and they approach their job and do what they always do, but they're talking as they do it. So he says, place a waypoint here. Waypoint's a 3D GPS coordinate, latitude, longitude, altitude. So place an anchor there and attach voice, video, photography to it. Then he comes over to this robot and he places another waypoint and attaches information. He comes over to the pliers, attaches another waypoint with information, and then takes the pliers and does the last step here of the process. And again, we're just trying to make this quick so as to save time. And he does step 4. Now we move on to an editor. So an editor downloads all that stuff and could use it just as is, but also could tidy it up a little bit, make sure everything was clear, add some text, and frankly, even if they want, publish it to a Word document. So one form would be put it back on paper or a PDF, but what's actually more interesting in the end is to deliver it to the new worker through AR. So that's the published output. Now here's Alexa, who is the new worker. So she puts on a HoloLens, fires up the same software now in the consumer mode, and it says, she says, I want to do the cobot failure test process, and it says, okay, go right over here to the right, and you'll see that anchor there. Go ahead and turn it just like the previous guy did. Okay, confirm you did that. All right, next step, come over here and move the cobot just like the previous worker did. Step 3 will be go over to the pliers after she confirms she's done with step 2. Then it'll take her over to step 3. She'll pick up the pliers, and I want to let this run to the end because I want to show you some analytics that come out of it. So she picks up the pliers, goes back over, removes the bit or whatever you call it on the front of the cobot, and then she's done. Now, what's interesting, though, I want to show you here in a second, is that we've captured data about how long each step took. That's very, very interesting because across the population of workers now, we have some analytics we can deal with. We can understand why are some workers better than others. We can also understand why is step 3 always so problematic, and could we go tweak step 3. So this is a great example of saying to your retired workers, congratulations, you get to retire. Just one last thing, please leave all your knowledge behind. And here's a way to do it that doesn't take much time than the normal work you do every day anyway. So it's a powerful concept. Okay, so on the people front, I've tried to convince you that AR, VR, coupled with video and other forms of analytics around instruction sets, really, frankly, turn people into cyborgs. You know, if you're old enough, or the right age, not too old, not too young, you'll remember the $6 Million Man featuring Lee Majors, or the counterpart that came out, The Bionic Woman featuring Lindsay Wagner. I loved those shows when I was a kid. But that's what we're talking about, is embellishing your human capabilities with unbelievable digital and electronic capabilities that really raise your game. Let me give you one last thing to think about before I close out on this. The best chess player in the world, at least some time ago, was Garry Kasparov. And IBM made a big deal when their computer called Deep Blue could beat Garry Kasparov at chess. And over time, I think it got to the point where it could beat him every time. So I'm a terrible chess player. But if I put on a HoloLens and sat across the coffee table from Garry Kasparov, and the HoloLens was watching the game, talking to Deep Blue around the best AI algorithms, what move should I make next, and then showing me, just like we showed in the example of the battery assembly or whatever, Jim, take this part and move it there, I would make every move almost instantaneously, and I would beat Garry Kasparov every time. And you'd say, this is the best player in the world. I'd say, no, actually, I'm terrible. It's just I'm guided through the process by amazing digital capabilities that sit up in the cloud that I used to be unable to use in this kind of a context. There's just no way to connect the two together. Okay, so that tried to share with you some thoughts about digital transformation and how it will profoundly affect products, processes, and workers or people. If you think about why is that important, you know, we're going to be able to create differentiated new products, whether it's IoT and digital stuff or AI and physical stuff. We're going to be able to introduce incredible process efficiency into production, supply chain, service, even engineering processes. And we're going to be able to deal with the problem we have with workforce turnover and skills and the cost of training and so forth. We're going to turn a lot of that kind of stuff completely on its ear. Now, just in closing, if you wanted to do all the stuff I've talked about here, let's just take a look at the technology you'd need to bring together. You would need to have CAD and PLM. That showed up many times. You'd need to have augmented reality / virtual reality, connectivity, IoT technologies. You need analytics and MES and automation and integrated, you know, sensors, networking, etc. So if you think of PTC and Rockwell together, we check all these boxes. And if you think of vendor A, vendor B, vendor C, vendor A is my competitor. They don't have any of the stuff Rockwell has except MES. And by the way, they don't have the IT/OT convergence suite either. If you think about vendor B, this would be a big company who competes with both of us, but again, many holes in their overall offering. And vendor C might be a typical Rockwell competitor who has none of this upstream stuff that PTC brings to the table. So I think that this partnership is made in heaven. It really is about the connected enterprise. It's about two companies who were headed the same place with appetites that were bigger than their stomachs, actually meeting each other, talking it through, and saying, wow, we shouldn't, you know, dream about competing with each other. We should align and produce the best suite out there and go really elevate the whole industry with a unique and very, very strong value proposition. So I want to thank you for this opportunity, Rockwell, Blake, others, and thank you for your patience as I went through my pitch. Hopefully you can see how much sense this partnership makes and how excited we at PTC are about it. Thank you.